Good morning, everybody. Going to go ahead and get started. I know some people are still signing on here. And I wanted to start today, and I had mentioned this yesterday, by going over the other form of quadratics for graphing. Yesterday, I covered one that was vertex form, and this one we're going to look at a standard form. And that's because we did all of this before Thanksgiving break. And now we have to try and remember that as we're getting to the end of the week here because next Tuesday, we have our test. Next Tuesday. So this one says we want a graph. Oh, I should mention, just pull out a sheet of paper. If you still have that sheet of paper from yesterday that we did the vertex form one on, maybe you still have some room on there for this one. Because again, really good review because we're working towards the actual test review on Friday and Monday. All right, so you'd want to write down graph y equals negative 2x squared plus 8x plus 1. And this is standard form. And the first little blank we're supposed to fill in is vertex and then axis of symmetry. So my question to you that I would like a volunteer to answer for is, how do we figure out where the vertex is when we have a standard form equation? If you know, unmute yourself. How do we find the vertex with a standard form parabola?
Negative b over 2a.
Excellent. Thank you, Emma. X equals negative b over 2a. So we go back up here and realize it's ax squared plus bx plus c, so my b value, and you might want to stop and do this. I know there are students that really like having those listed out. A is negative 2, b is 8, c is 1, and then put it into the formula. So negative 8 over 2 times negative 2, and 2 times negative 2 is negative 4. So we get an x coordinate of our vertex of 2. So far we can do this. Does anybody remember how we find the y coordinate? If you do, please unmute yourself and let us know.
Plug 2 back into the original equation.
Exactly. That's what this is for. You put in your x's and you get the y. So let's see what happens there. Negative 2 times 2 squared plus 8 times 2 plus 1. So we have to follow the order of operations and do the power first. So that'll give us negative 2 times 4 plus 8 times 2 plus 1. And then we can just multiply and divide left to right. So negative 8 plus 16 plus 1. And then add and subtract from left to right. Negative 8 plus 16 is 8, and 8 plus 1 is 9. We found it. Now that we have the vertex, we can also, and we actually could have done this earlier, write the equation for the axis of symmetry. So, somebody unmute and tell me what the equation for the axis of symmetry is, please. Again, the question is, what would be the equation for the axis of symmetry?
Isn't it just the x, so 2?
There we go, x equals 2. Yeah, because it needs to be an equation for a line, and just like we talked about yesterday, it's going to be a vertical line for all the parabolas that we do, and that would karate chop the x-axis. So x equals 2. Well, that's a good starting place. So make yourself, a little grid here, and find 2, 9. And now this is different than vertex form. And I'm really hopeful that I can find another couple of points. But generally, that's going to take a table. We do get one easy point, and that's always 0. Because when you have standard form parabolas, if you put a 0 in for x, you always get c. So this will be 0, 1. Because our axis of symmetry is at x equals 2, that means we can use symmetry, and our 0, 1 will also become 4, 1. But that would make me a little nervous on a test. I'd want to know, okay, well, what's going on here at 1 and at 3? So I would probably put a 1 into that and see what you get. So 1 squared is 1. 1 times negative 2 is negative 2. 8 times 1 is 8. Negative 2 plus 8 is 6. And 6 plus 1 is 7. 1, 7. And that's, again, buy one, get one free offer, because on the other side of the axis of symmetry, we would have another point. And that, I think, that's a pretty good look at this parabola. I think that's enough points. If you're careful and make sure that it's going to be like an upside down U, don't make it look like a V, because that's absolute value. Oh, that wasn't really straight. That's a little better. So there it is. There's our parabola. Very different way of graphing for standard form than there is for vertex form. Again, not necessarily horribly difficult. We just have to remember negative b over 2a. All right, let's keep going. We'll fill all the blanks in on this just like we did with yesterday's. So I need the domain of this little blue parabola here. All real numbers. Yes, all of our parabolas have all real numbers for their domain. But there was definitely a cutoff for the y's, so we have to figure out how to write that range. What should we put for range?
Y is greater than or equal to, less than or equal to -1.
What's our y value right here, Amos?
That's 8.
One more up. That was at 9. It was. So y is less than or equal to 9, because this one opens down. So our blue is using 9, 8, 7, 6, 5, 4, 3, 2, 1 to graph it. It's never going to get up here to 10. It's not going to make its way there. So there's our domain or range. All right, everybody, does this graph, my blue graph, does that have a minimum or a maximum?
Maximum.
It does. And what is that highest point?
9.
Yeah, we care about the y because we're talking about the highest point. Again, I wouldn't count it wrong if you gave me the ordered pair. Our vertex was 2, 9. So if you gave me that, I'd count it right. But really, it's about the y's. What's the highest or lowest y value that we could possibly have? All right, well, that's obviously not enough review, because we have the test coming next Tuesday. But I wanted to make sure we saw it at least twice again before we take the test next Tuesday. So let me set that aside and have you grab your notes packet for 4-5, which is still quadratic equations. The whole chapter is about us figuring out everything we possibly can about quadratics, which are parabolas, when we graph them. So far, when we graphed our parabolas, and we just did one of these, we were able to figure out where the vertex was. And then we had that nice little point, 0c, so we could figure out where the y-intercept was. But it would be good to have some other points that aren't necessarily a ton of work, something that we could find fairly easily without having to put it back into the original equation. And that's what we're working towards here. So this says with quadratic equations, we're going to solve quadratic equations by factoring. Now here's the big difference between what we've been doing and what we're going to do here. this word. So circle that word. When we say solve, that means we're not done when we factor. We still have to give them the solutions, and that's what we mean by solving, because then we can find where those solutions go on the graph. And we have another couple really easy points to find. So here in the graph, you're going to see that it says, hey, there's these things called zeros of the function. And they are here and here. And remember, the other point we had would have been 0C, so somewhere down here. That would give us a really great graph. We wouldn't need to put a lot of things in a table to make that happen. So the zeros of the function are always the x-intercepts. Where it crosses the x-axis. So they're always going to have coordinates something 0. So I'm going to put a question mark, 0. That's where we find those x-intercepts. So again, that's going to give us some really good information about our graphs. And we can kind of get away from having to use a table quite so much. So this one, it's kind of an obvious thing, but it's actually a property in math, the zero product property. And it says if you take two things and you multiply them together and get 0, something obvious has happened. So I start thinking, well, if you multiply these two together and you get 0, the only way to do that is if one of them is 0. And that's absolutely true. A equals 0, B equals 0, or they both equal 0. You know, they have to. That's the only way you can multiply two things together and get 0 is if one of them happens to be 0. So what we're going to do is going to feel like tremendous amounts of review about factoring. But we have to remember this word right here says we're not done when we factored. We have to keep going and figure out where it's going to hit the x-axis. So we want an actual number answer when we get done. So it says we're going to find the solutions of this quadratic equation. X squared minus 5x equals negative 6. Well, solving is also called finding the zeros. You can't do that unless you have a 0 on one side. We want to know where does this equal 0 for y. So like it says, our first step, get a 0 on one side of the equation. So we would add 6 to both sides and write x squared minus 5x plus 6 equals 0, because none of these are like terms. We can't put them together. This one's an x squared, this is an x to the first, and this is just a constant. Then, if we're lucky enough to find something that's factorable, then that's what we're going to do. So x squared minus 5x plus 6, there's no greatest common monomial factor. This is a perfect square, but 6 isn't. So we're at good old-fashioned factoring. We know that x times x will give us x squared. I'd like somebody to unmute and tell me the two numbers that multiply to positive 6 and add to negative 5.
Negative 3 and negative 2.
There they are. Thank you. Now, up until today, that would have been where we stopped because we were just factoring. But we want to know, when is this going to come out to 0? And here's what we just said about the zero product property. In order to get a 0, either this, x minus 3 has to be 0, or this, or both of them could be 0. Well, that's just going to take a little one-step solving. Here, add 3 to both sides, x equals 3. Add 2 to both sides, x equals 2. Pardon me. Those are the solutions, 3 and 2. So now the last thing we should do is check them and make sure that they give us 0. So our original equation, when we moved it over, was x squared minus 5x plus 6 equals 0. Let's check and see if these work. For 3, it would be 3 squared minus 5 times 3 plus 6 equals 0. Order of operations, you do the power first. So 9 minus 15 plus 6 equals 0. 9 minus 15 is negative 6. Yep, we did it right. We got a 0. And then we check the other one, the 2. So that would be 2 squared minus 5 times 2 plus 6 has to come out to 0. Order of operations, you do the power first, then we can do the multiplication. 4 minus 10 is negative 6, and negative 6 plus 6 is 0. So we know we're right. These are the two answers. Now on the graph, that means this is going to hit the x-axis at 3, 0, and 2, 0. So with graphing, that could help us out with 2 free points there. And they're not free because we did have to do some work to get to them. But at least it's not just plugging things in back into the table a lot. So there it is. So like I said, I'm going to have a feeling like, oh, this is exactly what we did yesterday. But if it says solve, if it says find the zeros, then we have to keep going all the way through and find the numbers that would make that true. All right, so we're already to the got it, which means this is the point where you're going to talk me through some stuff here. So let's see. The first got it says x squared minus 7x equals negative 12. I think there's something wrong with that. Somebody unmute and tell me what's wrong with that.
You got to add a 12 to both sides to get a 0.
We sure do. Solving is also called finding the zeros. It has to have a 0 on one side. All right, well, I don't see a greatest common monomial factor. First term's a perfect square, but 12 is not a perfect square. So that would mean we should be doing some good old-fashioned factoring if this is factorable. So I need somebody to give me the two factors. What's going to go in the parentheses here? Good. And now I realize I'm not done because this is important. I want to find the numbers that are going to make this 0. Now, most people are going to stop writing this down at some point and just go right to the answers because they're like, well, it's one step. I could just do this in my head. And some people just look at this and say, well, obviously it's 3 because 3 minus 3 is 0. Obviously it's 4 because 4 minus 4 is 0. There will be some that are a little tougher where we will want to write them out. But if you can go from this directly down to here, I'm not going to take off points. Just be careful that you don't do anything wrong, because if you do that, I can't give you partial credit for what you have there. So those are the two zeros. Again, perfectly checkable. I don't know that we want to do that. I think probably you're all feeling really good about your factoring after 3 days of factoring. I think you probably feel like you've got it. All right, let's look at the one that's to the right here. X squared minus 4x equals 0. That one has a greatest common monomial factor. What could we pull out of it? What do x squared and negative 4x have in common?
2.
No, there's no 2 in the x squared.
X.
Yeah, let's pull an x out. So this always bothers people because they're like, well, what do I do with that one sitting out here? Well, what would this have to be to multiply and give you 0?
0.
Exactly. So if there's any ever x's that are hanging out there all by themselves, you just put x equals 0. And then for this one, like I said, most of you are probably just looking at it and writing down x equals 4. But there it is, so that you're showing all the steps as you go through there. So that one, we did factor. We factored an x out. So we are still factoring to solve. Had the 0 already set up for us. So does this next one. 4x squared minus 25 equals 0 already has the 0 set up for us. Is there a greatest common monomial factor that we can take out of 4x squared and 25?
They're both prime.
So we can't do that. But wait a second, are they special?
Yeah.
They are. What are they?
2 and 5.
They're perfect squares. 2x squared and 5 squared. So how did they do this so that there's no middle term?
One negative, one positive.
Exactly. Exactly. Now this is why I said it's good to get into the habit of writing these down, because this one is a little tougher. This is going to take 2 steps to get each one of these. So we'll have to subtract 5 and then divide by 2. And on this one we'll have to add 5 and divide by 2. So it's not a bad habit to get into setting your factors equal to 0 so that when you get to tougher ones like this, you know, you don't go, oh my gosh, I don't know what to do now because you haven't practiced it. Alrighty, let's look at this one. 6x squared minus 19x minus 7. Oh boy, I hope I can divide that 6 out. Can I do that? No. Rats. Okay, well then it's obviously not a perfect square trinomial, right? Because 6 is not a perfect square and neither is negative 7. Oh, this is one of those combo problems. First times first, that would give me 6. Then I go to last times last, that would give me negative 7. And now I have to do that visual outside times outside plus inside times inside until I can find the pair that's going to add to negative 19. So see if you can find it.
3 and 2 and 1 negative 7.
3 and 2? Negative 21 plus 2? Pays to start at the bottom, doesn't it? They do that way too often in this book. All right, so we remember this came from first times first, last times last, and the order was important, so we always put them in there in the order that we have them. And then, like I said, you have to set it equal to 0 because this is a little tougher. Subtract 1 from both sides and divide by 3. And then for 2x minus 7 equals 0, we'll add 7 and divide by 2. Oh, that 7 looks kind of weird. That didn't make it much better. Again, totally checkable. We could put those back in there and we'd probably use a calculator because they're fractions. But we could put those back in for x and make sure that we get 0 when we put those values back in. Next one up here, 2x squared minus 72 equals 0. Well, at least it equals 0. Is there something, a greatest common monomial that we can pull out?
2.
Yeah, let's take it. Hey, x squared minus 36. I think we've seen that one before. That's a special pattern. How does that factor? How do you factor x squared minus 36?
X minus 6 and x plus 6.
Yep, that is a perfect square. Difference of two squares again, because this is x squared and this is 6 squared. Now, again, probably a lot of you will just say, okay, so x equals 6 and x equals negative 6, but we should get used to writing this step down in case they get a little more complicated. So, both checkable. Put the 6's back up in there. Better work. All right. I don't think that one that I just put the blue star in front of is ready to go yet. What do we need to do?
Subtract 26 from both sides.
Sure do. Gotta have a 0. All right, so x squared plus 11x minus 26 equals 0. Greatest common monomial factor? No, nothing we could take. So we're doing good old-fashioned factoring. Anybody have them already? Two numbers that multiply to negative 26 and add to 11.
13 and negative 2.
Yes. So we keep going because we're looking for the zeros. So we'd get negative 13 and positive 2. Those would be our zeros. All right, these two, they look a little heftier. So red star in front of that problem right there. Let's see. Greatest common monomial factor? Is there something we could pull out of all of those?
A 2.
Yes, and we have to do that. That has to be our first step. What it does is it makes the rest of the factoring easier. So pull a 2 out. Remember that that's like dividing everything that we see here by 2. Now, 2x squared is not a perfect square. 3 is not a perfect square. Oh, this looks like a combo problem here. But there's not a lot of try it numbers, because in the front we have a 2, and that's 1 and 2 and 2 and 1, and in the back it has to multiply to a positive 3 but somehow add to a positive 6. So we don't have a lot of choices here. So do you see it?
Two and 1 and 1 and 3.
6 plus 1. Not going to give us 12, is it? So does the other one work? 3 plus 2. Uh-oh. So here's what we just found. We just found one that can't be factored. Now here's why this is important. We're not done with this chapter. So we have to figure out, if it can't be factored, how could we find those zeros? How could we get them? And we're actually going to have two methods that we're going to learn in this chapter. One is called completing the square, and the other one is called the quadratic formula. So this one, right now, we would just have to write down can't be factored and move on. Let's go to this little doggy right here. You notice something wrong with that one?
Everything's on the right side,
Yeah.
except for the x squared.
So the question is, should I take all this negative stuff and move it over here with the positive 9x squared, or should I take the positive 9x squared and move it over there with all the negative stuff and make it negative? Well, it's usually a good decision to keep your x squared term positive. So I would add 48x and add 64 to both sides. Otherwise, you'd have to factor out a -1 out of everything before you started. Wow, those are some big numbers. Is there anything that we could factor out of a 9, a 48, and a 64? Greatest common monomial factor.
Can't you do, because the 9 and the 64 are perfect squares?
Good. That's what I want you to be thinking about is, well, do I want to? Because these are perfect squares. Maybe this is one of those perfect square trinomials. This is 3x squared, and this is 8 squared. So what we have to check is if you take 3x times 8, and then you take it times 2, or double it, do you get 48? Does it work?
Yeah.
It does. 3x times 8 is 24x, and 24 times 2 is 48. That makes it a perfect square trinomial. So that means we can write one binomial squared for this one. So what goes in the parentheses?
3x plus 8.
It does. And this is another one where we're glad we remember you can always set it equal to 0 and solve it, because this is going to take 2 steps here. So you subtract 8 from both sides, and then you divide by 3. So a lot of these had 2 zeros. This one only has 1. How come? Because of this. This power of 2 is something that we're going to talk about more in the next sections, but it's called the multiplicity of the 0. The rest of these, whenever we factored them, they just had a power of 1. Having a power of 1 means that it's going to cross the x-axis at those spots. When it has an even degree, this one is a 2, that means it's actually going to bounce off the x-axis, and it gets to count twice when that happens. So for any quadratic, because it's 2 for the highest power, you should find 2 zeros, unless it's a perfect square trinomial. And then you're just going to have 1 0 called a repeat 0, because it gets to count twice. So lots of factoring here. You've been doing tons and tons of factoring. And this, I think, is better with, do we want to do this tomorrow? No, let's do this now, because we're going to have more to do tomorrow. I don't want to make it even longer. We need to start talking about what happens when our answers don't come out perfectly. Because what I mentioned before was, if we can't factor these, what we have to do is use either completing the square or the quadratic formula to figure out where the zeros are, what the answers are. But that means we have to remember how to rationalize denominators, which I see in C right here, and simplify radicals. So A says the square root of 20. And we can't leave it that way. This page has me a little bit nervous. I remember thinking as I looked at it last night, you guys might not have done a whole lot of this because of last spring with COVID. Does anybody remember what we do to the square root of 20 to break it up?
Break it into 2 and 10.
We have to break it up, but we're going to break it into something that has a perfect square. So we need a,
5.
yes, 4 and 5. So what you do is you run through that list of perfect squares that we made the other day, and you think, all right, what's the biggest one that's going to divide into 20? And you don't go too far, because 2 squared is 4. So the square root of 20 can be written as the square root of 4 times the square root of 5. And then the square root of 4 is 2. So that's called simplifying the radical, pulling out anything that we can that's a perfect square and simplifying it. Now, B just says, what's the square root of x squared? Well, wait a second. When we solved before and we did this, what did that give us?
x.
Exactly. Those are inverses of each other. So if you have x squared and you want to get rid of it, you take the square root, and that gets you back to x. Now, this is the one here that's a little bit tougher. We've got the square root of 7/13. And people look at this and they go, 7/13, I don't know what the square root of 7/13 is. Well, that's not how we work the problem. What we do is we say, I'm going to separate those two. And I'm going to think of it as just the square root of 7 and the square root of 13. Now, if either one of those can be simplified, I should simplify them. So I think about my perfect squares that might go into 7. 1 doesn't do anything for us. 2 squared is 4. That doesn't go into 7. 3 squared is already up to 9, so there's no way that's going in. There's nothing I can do with that one. But that's not the issue. The issue is we are not allowed to leave radicals in the denominator. So square root of 13, start thinking about my perfect squares. A 4 is not going to go into it. A 9 is not going to go into it. 16, it's already too big. So how do I get rid of the square root of 13 in the denominator? Does anybody remember this from last year?
You square it.
In a way, yes. In a way, yes. Here's what we're going to do. We are going to multiply the top and the bottom of this fraction by the square root of 13 because that will give us the square root of 13 times 7 is 91. But on the bottom, it will be the square root of 13 squared. And now square root and squaring, those are going to cancel each other. So that'll just be a 13. Now, the square root of 91, we want to stop and think, can I simplify the square root of 91? So let's see, 9 times 9 is 81. That's not going to go into it. 8 times 8 is 64. That's not going to work. 7 times 7 is 49. Nope. 36. Nope. 25. And we can go through the whole list, but nothing's going to break up that square root of 91. So we would just leave that. So you can't leave a radical in the denominator. You can't have it in the bottom of the fraction. But if it happens on the top, it does. There's nothing we can do about that. Now, why is that important? Because as we get to higher level math, if you have radicals in the denominator, it really messes things up. So what we do is we call this simplifying and rationalizing the denominator to get rid of that. All right, D says the square root of -5. Square root of -5. So that means I want one number, and I want to write it in both of those spots and multiply them together and get a -5. Is that possible? If this is positive and this is positive, are they going to multiply together to give me a negative?
It's an imaginary number.
It is an imaginary number, which we haven't covered yet. So for us, what we would put is no real solutions. In a couple more sections, we're going to be able to write an answer for that using imaginary numbers, but not just yet. So that one is not possible. And like I said, this is what we're going to need as we get to solving by using completing the square and the quadratic formula later on. So that is where I'll stop. Tomorrow, we're going to find zeros by using the graphing calculator. So when you come, actually, I think when I write the update tomorrow morning, I'll try and remind you to have your graphing calculator with you if you have it. Otherwise, you're on your Chromebook, so you can use that app that's in Rapid Identity, and we can use that to figure out where the zeros are as well. So this we're going to hold off till tomorrow. Some nice word problems for us. So for 5-day 1, you need to do 9 through 17, all of those, and then 40 and 43 to 47. And remember, it's factoring, but then you have that extra step because we're solving of figuring out what those zeros are. So don't think you're done when you factored. You have to keep going. All about this word, solve. We have to know that solve means find the zeros, which basically to us means keep going. Figure out what those answers are. Oh, that might be in the blind spot again. That's probably better. Get out of the way here. So I saw a lot of.
I'll see you tomorrow.
Okay, bye-bye. I saw a lot of you already yesterday had that worksheet already turned in for all the factoring. So this assignment should go really fast for you as well if you've been doing all of that factoring.